Hello and welcome to section 4.13, where we're going to talk about the conformational dynamics of disubstituted cyclohexane molecules and their stabilities, as well as how to actually draw chairs from 2D bond line structures and bond line structures from chair conformations. And this is actually a really important skill that you need to be able to do because there can be several times when you need to take a bond line structure and convert it to a chair conformation in order to better understand what exactly is happening with the conformational energies there. So first, let's have a look at this cyclohexane drawing, and let's put a couple substituents on there so that we can start to talk about how to draw chair conformations, because that's the skill we're going to learn here. So first, let's draw maybe chloride there, and maybe the CH3 here. All right, so starting from this molecule, the first thing that I recommend doing is to draw in your hydrogen atoms. That way you don't lose track of them. There we are, there's one. And there's the other. Okay, so in general, whenever we're drawing cyclohexane molecules like this, we tend to say that the substituents on a wedge are up and the substituents on a dash are down. It might not make a lot of sense in a second, or right now, but it'll make more in a second. Okay, so when we go to put this in a chair conformation, that nomenclature of up and down is going to be important. Because looking at the chair, now perhaps it'll get a little more clear. So just for convenience, let's say that this carbon here is going to be this carbon. There we are. And so if the Cl is up, technically, that means of the two options, that is axial and equatorial, we need to use we need the Cl to be attached to the bond that is the most up or most vertical. And that is going to be this bond here. There we are, which means the hydrogen has to be on the most down bond or the less vertical bond, which is this one. Or sorry, the less pointed up bond, not the most vertical bond, because sometimes the down will be on a downward facing vertical bond. So the chloride is on the bond that is most facing up, and the hydrogen is on the bond that is most facing down. That's the two there. So then looking at the CH3 and the hydrogen on the next carbon, of the two options, we have the axial, and the equatorial here. We need to choose the bond that is the most up for the carbon, or for the CH3 to be. And that is this bond here. There we are. We'll just make that nice and orange. And the one that is most down is this bond, which is the hydrogen, right? Okay, so this is something interesting to note. So look at how these two substituents here are both pointed up, but in the chair conformation, one is axial and one is equatorial, right? So this is very key to notice that when you have two substituents and they are on carbons that are adjacent to each other, this relationship of up or up down can tell you kind of in a chair conformation where you expect them to be axial or equatorial wise in respect to each other. So that's just something to note, and there should be a tutorial video posted about this as well in UJ. All right, so then let's look at a chair conformation and go to a 2D structure. So let's draw our chair. Here's our V and our other parts here. There we are. That's not a bad looking chair. Okay, so in this chair now, let's say that we were looking at some situation that looked like this. So we have, there we go. Two bromines and a CH3. Now, the first thing I would do here is exactly like what we did in the previous example, where I would draw the hydrogens in that we're missing. That way we don't lose track of them. So that's an equatorial one. Well, I guess I drew that in the wrong place, didn't I? It's more, it should be, there we are. It should be parallel. This one should be perpendicular, and this one should be perpendicular. There we go. Okay. Now, in this case, oh, let's just get this fixed real fast. There we are. All right. So in this structure, now we want to take it to be in a bond line structure with wedges and dashes. There we go. Okay, and we need to arbitrarily assign one of these carbons a place on the newly drawn hexagon. That way we have a point of reference. So let's just say that this carbon is this one. All right. So it looks to me like the CH3 is up. And so that says that the CH3 should be on a wedge. And the hydrogen should be on a dash. There we are. And going to the right, one carbon, to see the bromine and hydrogen, it looks like that bromine is also on the up position. So it should be on a wedge here. And the hydrogen should be on a dash. The bromine that is 1, 2, 3, 4 places away from the original carbon that we chose. Oh, I drew that in the wrong place, the second one. I'm sorry. I put it on the third carbon instead of the second one. That's silly. Here we go. This is where the bromine goes. There we are. All right. So then now the bromine on the fourth carbon looks like it is pointed up as well. And the hydrogen is pointed back. So there we have it. From a bond line conformation, or a bond line structure to a chair conformation, and from a chair conformation to a bond line structure. Great. So now that we have that skill in our back pocket, let's look at the stability of different chair conformations. So going from now a bond line structure, we can put in some substituents. There we are. Okay, so the first thing that we do again should be to put in those hydrogens so that we don't miss them. This one's on a wedge, and so is this one. They're both going up. And if we draw the chair conformation of these, we can see, here's our chair. Okay. If we draw the chair conformation of these, seeing that this carbon is corresponding to this one, we'll see that the hydrogen is pointed up and the CH3 is pointed back or down. And on the third carbon away, we also see the hydrogen is pointed up and the CH3 is pointed down. So when we're looking at the energy of conformations, we have to be able to do the ring flip that we learned about in section 4.10, I believe, or maybe it's 4.11. Is it 4.11? Yeah, it's 4.11. Or is it? No, it's 4.12. I'm sorry, it's 4.12. So we learned about the ring flip in 4.12. There we go. Ring flip, which if you remember means taking the footrest up to make it the backrest and taking the backrest down and making it the footrest. And in doing so, axial becomes equatorial and equatorial become axial. So doing that, we make the opposite ring, right? Oops. There we go. And so now what is once down is up. Or sorry, they remain, sorry, what was up remains up, but what is once axial is now equatorial. So in this structure, the CH3 is now axial, whereas before it was equatorial. And the hydrogen is equatorial. And in the other, the hydrogen is equatorial, while the CH3 is axial. And hopefully in your mind now, this is triggering alarm bells, thinking about the energy present in these two, that these two molecules have inherent to their systems. The cyclohexane chair conformation on the bottom is very different than the one on the top, right? Because as we learned about in our previous chapters or sections on cyclohexane, there is a significant strain interaction between these two axial substituents that are present at the 1 and 3 positions of a cyclohexane, right? They're called the 1,3 diaxial interactions. I'll just write it here so that we remember. There we are. 1,3 diaxial interaction there. So because of that 1,3 diaxial interaction, there will be a higher energy for that conformation. And so putting the substituents in an equatorial position is much preferred over an axial. As substituents get larger, this this motivation gets much larger too for molecules. So the rule should be for you that if you can, put substituents in an equatorial position. And if you have to do a ring flip to make that happen, then go ahead and do it, because equatorial substituents are typically the lower energy conformers in comparison to the axial versions. So you can read more about these in section 4.13, and we are finished with that section.